Today we will introduce surface integrals. These are like line integrals where we integrate a function over a curve, but here we're going to integrate the function over a surface. Also like line integrals, there will be two forms of surface integral, one where we integrate a scalar function and one where we integrate a vector field. We're going to start with the scalar function. So let's say we have a surface S with the parameterization R of uv, where u and v are over some domain d in the uv plane. So we have our, say in the uv plane here, we have some domain d, and that gets mapped onto some surface in three-dimensional space. We're going to have a function f of x, y, and z, so some function of our three-dimensional space, giving us values, real numbers as values. And we're going to approach this the same way we did surface area in the last section, where we take small rectangles in D. So let's say this is a rectangle Rij. This maps onto some section of our surface. Maybe we'll call this Sij. And we'll essentially take a sample point of Sij, the value of that function at that point, and we'll multiply it to the area of Sij. So in a sense, what we're doing here is taking some, I guess the point maybe is Pij. We take that point, plug it into our function, multiply it by the area, which we'll denote by delta Sij. That's the area of this, which depends, of course, on the rectangle. We want to add up a whole bunch of these. So as we divide D up into a bunch of little rectangles, that divides S up into a bunch of little sections, and each of those has a particular value. And so when we add those all up, of course, I wrote this as Ij as our indices because we have a full grid, a two-dimensional grid of these things. We have to add up over all of those. So you can see this is going to be some sort of double integral as we go. As we take the limit, this turns into what we call the surface integral of f over the surface S. So I just write this as, we write it with the double integral. We put the name of the surface below that, we put our function there, and we put ds. So just like with line integrals, we put d with a little s, here we're putting a d with a capital S. That's just an notation for surface integrals. And it's just going to be the limit of this Riemann sum. Of course, we don't want to have to evaluate integrals using Riemann sums, so we're going to use the result from last section, that the area of this Sij is going to be, this delta Sij is approximately equal to the magnitude of the cross product of Ru and Rv times delta U delta V. Or in essence, our Riemann sum over here is approximately the Riemann sum where we have f of Pij, we have the magnitude of Ru cross Rv at Pij with delta U and delta V. Kind of running into myself there. But that allows us to essentially turn this surface integral into a proper double integral over the domain D. And this is going to be the formula that we're going to be using, where we have take our surface integral by taking the cross product of Ru and Rv, using it as the magnitude, and just essentially putting it into our double integral just along with the function f evaluated at the, essentially the composition between f and r. Just treating f as a function of u and v instead of x, y, and z. In the special case of a surface given as a function of two variables, I don't want to use f here, so I'm going to use g. So we have z equals some function g of x and y. Recall that we found surface area over a region D in the xy plane by the formula a of s is the double integral over over that domain D of the square root of the derivative of g with respect to x squared plus this derivative of g with respect to y squared plus 1 dA. And because all that's really different between the formula for surface area and the formula for surface integrals is that for surface integrals we do have the function in here. So essentially for this kind of thing, we're just going to put in a function into the integral, and so we end up with this particular formula here. Now they changed from putting the function name g, and they just went ahead and put z there. I mean, it's the same kind of thing. We're taking the derivative of this formula, z equals some formula in terms of x and y, though they do have the g here as well. But the point here is that any of our techniques that we developed for finding surface area can be turned into a way to take surface integrals, because the big thing there was being able to compute the magnitude of RU cross RV. Another thing that we want to note here is that when we take surface integrals and we integrate over surfaces that are not entirely smooth, think in terms of, let's say we have a box where we want to integrate over all the sides of the box, or maybe over a cylinder where we might want to include the top and bottom of the cylinder. In those cases, we have a surface that does have some corners to it, but we can view it as a finite number of smooth pieces. Each face of the box is a smooth surface. They're all planes, in fact. Two of the surfaces for our cylinder are planes, and one is just an actual cylinder. That's the cylinder piece itself, but it is just a curved plane. But once we can do that, we can essentially break up our surface integral into a finite sum of surface integrals over the smooth pieces. So the surface integral over the entire thing, the total surface integral, is just going to be the sum of the surface integrals over each piece. Notice that we did have a similar result for line integrals, where we're able to take a piecewise smooth curve and do each of the pieces separately and add the results together. And that turned out incredibly useful when we talked about Green's theorem. And it shouldn't be too surprising that this result for surface integrals will also be useful for Stokes' theorem and the divergence theorem that we'll cover in the next two sections. Let's move on to some examples, though. We'll start with problem 7. Here we want the surface integral over the function just y over the surface that is the helicoid with the vector equation r of uv is u cosine v, u sine v, and v, where u is between 0 and 1, and v is between 0 and pi. Now, in the last section, we actually looked at this helicoid, and we can actually go ahead and plot it, so maybe we'll be reminded of what this looks like. So this was u cosine v, u sine v, v, where u goes from 0 to 1, v goes from 0 to pi, and we have this surface here. We want to integrate y over that surface. And recall that we actually did a lot of the work there, so I'm just going to kind of skip to what we did. If you want to take a look back at how we did that, that was the last problem that we worked on. So it would be in the third video. But we found that r sub u cross r sub v was equal to sine of v I minus cosine of v j plus u times k, and that the magnitude is equal to the square root of 1 plus u squared. Since we're trying to take the surface integral of y. We're basically going to use these as our limits for u and v. I'm going to put the v ones first. I need to replace y with what it is in terms of u and v. So y is equal to u sine v. And that's what I need to put in here. Then I need to put in my magnitude of RU cross RV. And then I just put my limits. So have the U ones here, and then the V ones. Now this actually turns out even easier than when we had to find the surface area of it. So the fact that we have a U here from Y actually helps if we want to do a substitution for the U. In fact, I'm going to set W equal to 1 plus U squared, which means that dW equals 2U du, and that we have the U there for that derivative. I'm going to have to introduce a 1/2 though. So I'm going to have a 1/2 sine V. I'm going to have a square root of W dW dV. Though I do need to change my limits, don't I? So 0 and 1 were for limits for U. When we plug in 0 and 1 in here, for 0 we get 1, for 1 we get 2. Go ahead and take the integral square root of W. Remember, that means we raise the power by 1. So a power of 1/2 becomes a power of 3/2. We end up having to divide by the new power. So we have a 1/2 divided by 3/2. Turns into a 1/3. We still have the sign of V in there. And we need to evaluate this from 1 to 2. That becomes, well, we saw the 1/3, we saw the sign. In fact, we can go ahead and maybe deal with the sign by itself. So all the stuff involving the 1/3 and the W, those are actually don't involve V anymore. So we'll go ahead and integrate the sine of V. That becomes a negative cosine of V, evaluated from 0 to pi. The stuff involving the W to the 3/2, 2 to the 3/2 is going to be 2 square root 2. Then we subtract 1 to the 3/2, which is 1. When we evaluate cosine of V at pi, we get a negative 1. So we actually get a positive 1 because of the negative that's already there. Then we subtract a negative, so add cosine of 0. Let's just write this out. We have a 1, but then we subtract a negative, so add cosine of 0, which is a 1. So we end up getting to multiply by 2 for this integral here. Or in other words, what can we do? We can just write this as maybe 2/3 times the quantity 2 square root 2 minus 1. That's about as simple as you can actually write that one, I guess. But that is the integral of y over this particular surface. Moving on to problem 13. This time we're again integrating something not too complicated. We're just integrating z squared over the surface x equals y squared plus z squared, where we're specifically saying that x is between 0 and 1. So if we go ahead and plot that, so x equals y squared plus z squared. As I said, that's a paraboloid. We're only looking from x equals 0 to x equals, well, I could put in x equals 0. That's just, obviously, the paraboloid doesn't even go past that anyways. But then we go to x equals 1. So we're only looking at this piece, the tip of our paraboloid. I don't really need that part, I guess. So we're only looking at that part of it. We do need to come up with a parameterization for this, though. One thing that we could do, so one possibility, We could just let y equal u and z equal v, which means that x is equal to u squared plus v squared. Then we'd have to integrate this, where we'd have to integrate over the disk x squared, sorry, not x squared, u squared plus v squared is less than or equal to 1. That's something we could do. We'd probably want to use polar coordinates to do that. But we could also kind of skip having to do polar coordinates later by just taking some inspiration from polar coordinates right now. We could basically just set y equal to r cosine theta, z equal to r sine theta, which case the x, because we're taking y squared plus z squared, the cosine squared plus sine squared will go away. We'll be left with the r squared that was multiplying both of those. And of course, in this case, we are allowed to have theta go from 0 to 1. And since x is equal to r squared, and x is going from 0 to 1, that just means that r is going to go from 0 to 1. I'm going to go ahead and use this, though both of them will actually work out, and you'll end up with the same integral at the end. So it doesn't actually save us any space or any effort to actually do one over the other. Now we do need to find out what the r sub u cross r sub v is. In this case, we're actually using r and theta. This r here is not the same as the actual vector r. If you want, we could actually go ahead and write it with an r with an arrow over it. So in this case, we have r with an arrow over it is r squared I plus r cosine theta j plus r sine theta k. This is these written out in coordinates. R sub r, different r's here. We're taking the derivative with respect to r. That gives us a 2r there for the I, a cosine theta times j, and a sine theta times k. And r sub theta, well, there's no thetas here, so that's 0. Here we get a negative sign, but we have an r, so a negative r sine. And here we have an r cosine. We do need to take the cross product of these. I'm going to drop the arrow. I don't like writing arrows over things. I'm also going to write the r sub r as this is going to be my middle row. I'm going to put it first, just because it's the kind of the longest one. We have a 2r, we have cosine theta, we have sine theta. Then we put on our last row, we have a 0 because there's no I. We have minus r sine theta. We have r cosine theta. And our top row, we just put ijk. And I'm going to kind of skip writing out the actual expansion along the first row. But the I component, we're dealing with this 2 by 2, which means that we take cosine theta times r cosine theta minus sine theta times negative r sine theta. That's going to give us an r in both of them. The first one's going to have a cosine squared, and because we're subtracting negative, we're going to be adding that to a sine squared. In other words, we just have an r. R times I is our first component. For j, we're going to go 2r times r cosine theta minus sine theta times 0. So 2r times, well, actually 2r squared cosine theta. Keep in mind, since it's a j component, we are subtracting it. So we end up with a negative 2r squared cosine theta times j. Finally, for k, now we're dealing with this 2 by 2 over here. We have 2r times negative r sine theta minus 0. So we end up with a minus 2r squared sine theta k. And of course, it's not a coincidence that we end up with a very similar form for j and k. when we take the magnitude of this, because that's what we're going to need for our surface integral, we're just going to square all these and add them together. Of course, everything here has an r in it already. I'm going to pull that r out. So this one, actually, we're just taking the square of 1. We're going to add it to the square of 2r cosine theta, because we had 2 r's there. So we have a 4r squared cosine squared theta. And then same thing here, we have a 4r squared sine squared theta. Or in other words, because these both have 4r squared in them, the cosine squared plus sine squared gives us 1, and we get r times the square root of 1 plus 4r squared. Now we're going to take that and we're going to use it in our surface integral. Remember, we are integrating z squared, and recall that z here is r sine theta. So our surface integral over s of z squared ds. Remember that we're taking theta from 0 to 2 pi. We're taking r from 0 to 1. Z squared, we have r sine theta squared. And then we had r square root of 1 plus 4r squared from our magnitude of r sub r times r sub theta. That's dr d theta. I'm going to go ahead and actually split this up. So what we have here is we have things that involve r and things that involve theta, but they're being multiplied together. So I can actually split this into 2 separate integrals and not have to deal with them both at the same time. So for the theta part, note that we have a sine squared, and that will just be by itself. For the r part, we have an r squared. We have another r here. I'm actually not going to combine those because we're going to deal with them with a substitution where it'll actually be easier to have those split apart. When we're integrating sine squared, we do need to use the power reduction formula. So remember, sine squared is equal to 1/2 minus 1/2 cosine 2 theta. For the r, I'm going to use the substitution of, let's say u is equal to 1 plus 4r squared, which means that du is equal to 8r dr. So we have an r here, which will deal with one of these r's. The other 2 r's that are here, we're actually going to take our equation for u, our initial equation for u, and we're going to solve for r squared. Essentially, if I take u minus 1 and I divide that by 4, I get r squared. So here I'm going to replace that with a u minus 1 over 4. I'm going to replace the r dr with a 1/8. And I still have a square root of u. But this will be a lot easier than what we had up here, because we can actually turn this into a power of u and distribute it to the u and the 1. Of course, I do have to change my limits. A 0 gives me u equals 1. A 1 gives me u equals 1 plus 4, so we get a 5. Alright, now we go ahead and integrate this. Integral of 1/2 is 1/2 theta. Integral of cosine is a sine, but we have to deal with the 2 that's in here by dividing it. So we end up with a 1/4 sine of 2 theta from 0 to 2 pi. For this one, I'm going to actually pull out the 4 and the 8 on the bottom. We have a 1 over 32. We're taking the integral from 1 to 5. The square root of u is u to the 1/2. When we multiply it to u, I get u to the 3/2. And when I multiply it to the 1, I get just u to the 1/2. Alright, here. Sine of 4 pi is 0. Sine of 0 is 0. So actually this part is going to cancel out either way. But when I take 1/2 of 2 pi, I get pi. And when I take 1/2 of 0, I have 0. So actually, this part turns into a pi. I still have the 32 on the bottom. The integral of u to the 3 halves, I raise that 3 halves to a 5 halves, and I divide by that new power, so I get multiplied by a 2/5. Same thing here. 1 half becomes 3 halves, and I end up having to multiply by 2/3. Taking that one from 1 to 5. Essentially means I have, what, 2/5, 5 to the 5 halves. That's actually, you could say that it's 5 squared times square root of 5. I mean, that's essentially what 5 halves is. It's actually, you could say, is u squared times the square root of u. So I'm going to have 5 squared. Actually, I'll even just write that as 25 square root of 5. We have, when we plug 5 into here, because u to the 3 halves is u times square root of u, we have 2/3, 5 times the square root of 5. And then we get to do the same thing for 1, except now the actual powers are going to be easier. They're both 1 in this case. But we're going to be subtracting a 2/5, and because we're subtracting already, we're going to be adding a 2/3. And then what I'd like to do here, because this looks really ugly to me, I go ahead and pull out all the denominators. So I'm going to pull out the 5 and the 3. I'm going to also pull out a 2 because everything has a 2 in it. And that does simplify things quite a bit. And it does allow me to combine my two powers, my two square roots of 5, just combine the like terms there. Ultimately, after a bunch of simplifications, I solve the pi. My denominator gets changed to a 120, and on the inside here, I have a 25 square root of 5 plus 1. So, if you want, you can try to figure out how I got to that. But I think that's the nicest way of writing it. There's not really better ways of doing that one. So that is the integral of z squared over the tip of this paraboloid. Let's do one more example of these kind of surface integrals. We're going to look at the integral of xz over the surface where S is the boundary of the region enclosed by the cylinder, y squared plus z squared equals 9, and the planes x equals 0 and x plus y equals 5. As you can probably tell, they've actually not really picked any complicated functions to integrate. The majority of these problems are really testing on whether or not we can set up the surface part of the surface integral. And in this particular problem, we need to deal with multiple pieces. So this will be actually a fairly complicated problem just because of that. So remember, we're looking at the cylinder x squared plus y squared is equal to 9. So we have this surface here. But we're not looking at the entire thing. We're going to be bounding it by x equals 0, and then also x plus y equals 5. Okay, I see what I did wrong here. I've got myself a little confused. The cylinder that we're looking at is not x squared plus y squared equals 9. It's y squared plus z squared equals 9. Okay, that makes a little bit more sense to me. So we have this cylinder. Essentially it has a bottom. I'm going to refer to it as the bottom just because it would make a little bit more sense to position the cylinder vertically, even though that's not what they gave to us. But I'm going to refer to the bottom here down on the YZ plane. And then we have a top that's actually at an angle. And when they're telling us that the surface is the surface that over this entire volume and not just the surface of the cylinder itself. So we're going to have to deal with the top, the bottom, and the side being the actual cylinder. And those are going to be 3 different surfaces that we're going to have to integrate over, and then we're going to add the results together at the end. Let's start with the bottom. So we're starting with the x equals 0 plane. I'm going to call that S1. Note here, since x equals 0, the integrand is just 0. So we're taking the surface integral over S1 of 0 ds, which is, of course, just 0. That one's pretty easy. Let's now move on to the top angled plane of x plus y equals 5, which I'm going to go ahead and call S2. Now we can actually view this as a function. We can view this as the graph of the equation x equals 5 minus y over the disk y squared plus z squared equals 9. So we're kind of switching the roles of x and z, but we can go ahead and use our alternate formula here, where we basically put the g of yz in for x rather than a g of xy in for z. But it's the same idea. So we have the surface integral over S2 of xz ds. It's going to be the integral. Well, we do have to deal with the being over disk. I'm just going to write it as over d for the moment. Keep in mind that the x is going to be replaced by 5 minus y because we're going to be integrating over z and y. The z we can just leave alone. Then we have the square root of 1 plus the derivative of x with respect to y. So I'll go ahead and even write that out. So derivative with respect to y of 5 minus y squared. But then we also have the derivative with respect to z of x, or 5 minus y squared. That'll be dA, where that's going to be a dy and a dz in whichever order we put it in. Of course, here, the derivative with respect to y of 5 minus y is negative 1, so we have a negative 1 squared. The derivative of 5 minus y with respect to z is just 0, because there's no z's in there. So actually, this square root turns into the square root of 2. We have 5 minus y z times the square root of 2 dA. And then, since we're integrating over a disk, we're going to go ahead and use polar coordinates. We're working in y and z instead of x and y, so I'm going to go ahead and make y equal to r cosine theta, and z is going to be r sine theta. Either direction actually works, and you'll get the same result either way. Of course, we are going over the disk of radius 3, so theta is going to go from 0 to 2 pi, r is going to go from 0 to 3. We have 5 minus r cosine theta. Z becomes r sine theta. We do have the square root of 2, which I'll go ahead and pull that out. And since we are swapping from y and z to r and theta, we do end up having to introduce an r as part of switching to polar coordinates. Alright, now we need to do the integration. So I'm going to go ahead and expand this out. So we'll have a 5 times r squared sine theta minus, well, we don't have a 5 there, but we do have 3 r's that are going to have to be there, times sine theta times cosine theta, dr d theta. Now we could go ahead and just do this directly, integrate with respect to r, but since I know this is going to actually save us a little bit of work, I'm going to actually do theta first. Because we just have constants here, we're able to swap the order as much as we want to. So I'm going to first integrate with respect to theta, and I'm going to make a substitution there. I'm going to make the substitution of u equals cosine theta. That means that du is equal to negative sine theta d theta. And so the sine theta that we have here and the sine theta that we have here will both be part of our derivative. We do have to introduce a minus sign, but that's okay. And I'm also going to move the part with the r to the outside. But this will turn into a 5r squared with no sign, because that's been absorbed into our derivative, minus r cubed. This sign gets absorbed into the derivative, and this is just u. du dr. Now we do have to change our limits. And our limits, we take the 0 and the 2 pi, and we plug them into our formula for u. Cosine of 0 is 1. Cosine of 2 pi is also 1. So we have the integral from 1 to 1. Well, what does that mean? That means our integral on the inside here is 0. It's automatically 0. So we integrate 0 from 0 to 3. We're still going to have 0. This whole thing turns out to be 0. Kind of having a pattern here. Hopefully the other one doesn't turn out to be 0. But our last piece, which we'll call S3, that's going to be the actual side of the cylinder. What I'm going to do is take a cue from polar coordinates still. So here, our side of the cylinder. It's going to be S3. And I'm going to let y equal 3 cosine theta, z be 3 sine theta, because those will give me points on the circle of y squared plus z squared equals 9. I mean, that's why we have a 3 here. The 3 here is because 3 is the radius of the cylinder. I'm just going to let x be itself. I'm not even going to give it another label. I'm just going to keep calling it x. The limits aren't just going to be numbers this time, unfortunately. So x is going from 0 up to this plane, and that plane is given by, remember, our plane was x plus y equals 5. That means that the top of x is going to be 5 minus y, where y is 3 cosine theta. So x goes from 0 up to 5 minus 3 cosine theta. Those are going to be my limits. I do need to find out what r sub x and r sub theta are. So remember, r is just the vector with these as its components. So r sub x, well, the only thing that involves x is x. So I'm just going to get I plus 0, j plus 0, k. R sub theta, well, there's no thetas in x, so that one's 0. But we do get a minus 3 sine theta for j, and a plus 3 cosine theta times k. When we take the cross product of these, it's actually pretty simple, just because r sub x turned out to just be I. We're just taking the cross product of I with j and I with k. The cross product of I and k actually turns out to be a negative j. Remember, we're going in the wrong order there. So we're going to end up with a negative 3 cosine theta j. Cross product of I with j is actually positive k. So we're going to get a negative 3 sine theta k. The magnitude of this, we're taking negative 3 cosine theta squared plus negative 3 cosine theta squared. Well, cosine squared plus sine squared, of course, is 1. So we end up with the 3 squared, but we're taking the square root of that, so we just get 3 overall. So at least that part is actually pretty nice and simple. And our integral over S3 of xz ds, so be the integral from 0 to 2 pi. So theta is still going from all the way around the cylinder, so 0 to 2 pi. X is going from 0 to 5 minus 3 cosine theta, as we saw before. X just stays as x. Z gets changed to a 3 sine theta. We multiply by the 3 from here, and we have dx d theta. We go ahead and integrate this. The x here becomes a 1/2 x squared, which is then going to be replaced by the 5 minus 3 cosine theta. So I'm going to go ahead and just take the 1/2 that squared, so 5 minus 3 cosine theta squared. I'm going to move the 3 over to here, and I'm going to have the sign that's still left from here. Actually, I guess we have another 3 there, so I should change this to a 9/2. And d theta. And now I'm going to do kind of a trick that we did just a minute ago. I'm going to let u equal cosine theta, so that du equals negative sine theta, d theta. That means this sign that's sitting on the outside is part of our derivative. We're going to have to introduce a negative, but that's okay. So we'll have a negative, we'll even pull out the 9/2, or the integral of this thing, which it turns into a 5 minus 3 u squared. Sine theta d theta basically becomes our du. Our limits, well, we actually did limits from 0 to 2 pi just a moment ago for u equals cosine. Both of those turned into a 1. So again, since we're just integrating from a number to itself, we get 0 again. Well, that was a lot of work to get zeros, but the point here is that the surface integral over the entire thing of xz ds is equal to the sum of those 3 zeros, or 0 overall. This problem might have been a little bit more interesting if it had been what I originally thought it was. If this was x times y instead of x times z as our integrand, we actually get something other than 0 at the end. But it is what it is. Alright, in the next video, we're going to start trying to talk about integrals of vector fields over surfaces. And yeah, so that's what we're going to try to do that in the next video. Meet me in that one.